Hello everyone and welcome back to Sumantra Codes. Today we are going to surgically dismantle the most critical component of a neural network. We are going to talk about the decision makers, the spark, the activation functions. If you have been following this series, you know that the neuron takes input, multiplies them by weights and adds a bias. That is the linear step. If we stack thousands of layers of these neurons without activation functions, what do we get? We get nothing new. We get a single linear regression. Without non-linearity, a deep neural network, no matter how deep, compresses into a single layer. All that computing power is wasted. The deep in deep learning essentially vanishes. So this lecture is about escaping the linear trap. We are going to cover the mathematical history and the practical reality of activation functions. This is a long one, so grab your coffee, let's get to the board. To understand where we are going, we have to look at where we started, the human brain. In 1943, Warren McCulloch and Walter Pitts proposed the first mathematical model of a neuron. Their logic was binary. Think about a neuron in your brain. It doesn't output a maybe. It doesn't send a kind of signal. It either fires or it doesn't. It accumulates electric potential from its dendrites, and if that potential crosses a specific threshold, boom, it fires an action potential down the axon. This is the Heaviside Step Function. It is brutally simple. If your weighted sum is positive, the output is 1. If it's negative, the output is 0. This logic gave birth to the perceptron, and for a while, we thought this was it. We thought we could model intelligence with just on or off switches. But there was a massive problem. Deep learning relies on backpropagation. Backpropagation relies on gradient descent, and gradient descent relies on derivatives or calculus. Look at the step function on the screen. What is the derivative or the slope of a horizontal line? It's 0. What is the derivative at the vertical jump? It's undefined or infinite. So, if you try to train a network using a step function, your gradients are essentially 0 everywhere. The network can't learn. It doesn't know which direction to move the weights because the slope is flat. It's like trying to find the bottom of a valley, but the entire world is flat plateau. You have no information on where to go. We have nothing. We needed something smoother. We needed curves. Enter the sigmoid function. This was the king of activation functions for decades. Look at its shape. It's beautiful, isn't it? It takes any real number from negative infinity to positive infinity and squashes it into a range between 0 and 1. This solves our derivative problem. The curve is smooth. It's differentiable everywhere. We could finally use calculus to update our weights. But more importantly, it gave us a probability-like interpretation. An output of 0.9 could mean 90% confident this is a cat. This is why sigmoid is still used today, specifically at the final layer in the binary classification problems. However, as we tried to build deeper network in 1990s and 2000s, sigmoid revealed a dark side, a fatal flaw known as vanishing gradient problem. Pay close attention to this. This is the derivative of sigmoid. Sigmoid x into 1 minus sigmoid x. Notice that the maximum value of this derivative, it is exactly 0.25. Now imagine a neural network with 10 layers. In backpropagation, we use the chain rule. We multiply the gradients of each layer together as we move backward from the output to the input. If you have 10 layers and the maximum gradients you can pass through is 0.25, what happens? You are multiplying 0.25 times 0.25 times 0.25 10 times. So it's 0.25 to the power of 10, which is roughly 0.0000009, which is very close to 0, and the signal dies. The weights in the early layers, the one responsible for detecting edges and basic features, stop updating. The network stops learning. The deep network becomes effectively shallow because of the last few layers are actually training. We try to fix this with Tanh or hyperbolic tangent. Tanh is basically a scale sigmoid that goes from -1 to 1. It is a zero-centered, which helps with optimization because the data doesn't drift to positive values constantly. But guess what? Tanh suffers from the exact same problem. If the input is very large or very small or saturated, the slope becomes 0. The gradient vanishes. We are stuck. We need a revolution. So in 2011 to 2012, everything changed. Researchers, notably Glorot, Bodes, and Bengio, popularized something that looked ridiculously simple, almost too simple to work. the Rectified Linear Unit or ReLU. It's fx equal to max of 0 or x. That's it. That is the entire function. If the number is negative, make it 0. If it's positive, keep it as it is. When this was first proposed, people were skeptical. It's not a curve, they said. It's barely non-linear. But let's look at why ReLU saved deep learning. First is computational efficiency. Calculating an exponential function like e to the power minus x for sigmoid is expensive for a computer. Calculating max between 0 and x is simple check. It's lightning fast. When you're training on billions of parameters, this speed difference is massive. Second is no vanishing gradient in positive regime. What is the slope of line y is equal to x? It is 1. Regardless of how high the input x is, whether it is 10, 1000 or a million, the gradient is always 1. It does not vanish. This allows us to train networks that are hundreds of layers deep, like ResNet, without the signal disappearing. Third is the sparsity. Because ReLU outputs absolute 0 for all negative inputs, it forces many neurons to be inactive at any given time. This creates sparse representations. It turns out this is very similar to how biological neurons work. Your brain doesn't fire every neuron in every stimulus. This sparsity makes the model more robust and efficient. But ReLU isn't perfect. It has a bug called Tanh ReLU problem. Look at the negative side. The slope is exactly 0 if a neuron gets stuck in this negative zone, maybe due to large learning rate update. It will never recover. The gradient will always be 0, the weights will never update, and that neuron is effectively dead forever. To fix this, we have a variant like Leaky ReLU. Leaky ReLU allows small gradients like 0.01 for negative values. It keeps the neuron on life support, allowing it to eventually learn its way back into the positive zone. If you look at the source code of BERT, GPT-3 or Llama, you won't usually find standard ReLU. You will find GELU or Gaussian Error Linear Unit or Swish. Why? Nature hates sharp corner. The kink in ReLU at exactly 0 is mathematical singularity. It's a harsh transition. Swish proposed by Google Brain is defined as fx is equal to x into sigmoid of x. GELU used in GPT is based on probability theory. It weighs inputs by their percentile in a Gaussian distribution. These functions combine the best of the both worlds. They look like ReLU or linear for large positive values, so they don't have a vanishing gradient, but they're smooth around 0, allowing for a subtle negative values. This smoothness helps the optimization landscape, allowing the optimizers like Adam or SGD to navigate complex loss surfaces more easily. If you're building a transformer today, you'll use GELU. If you're building a vision model like EfficientNet, you likely use Swish. Before we go, I want to address a question which I find very relevant. How do we differentiate ReLU at 0? As I mentioned, the derivatives of ReLU is 1 for x greater than 0 and 0 for x less than 0. But at exactly x is equal to 0, the derivative is mathematically undefined. It's a sharp corner. So how does PyTorch or TensorFlow handle this during backpropagation? If your input happens to be exactly 0.00000, does your training crash? The answer lies in the concept called subgradients. In convex optimization, if a function is not differentiable at a specific point, we can pick a valid subgradient from a range of possible value. For ReLU, at 0, the slope could be theoretically anything between 0 and 1. In practice, deep learning framework makes an arbitrary choice. Usually, they set the gradient at the 0 to be 0 or sometimes 0.5. It actually doesn't matter because in floating point architecture, such as 32-bit or 16-bit floats, the probability of your weighted sum hitting exactly 0 with infinite precision is statistically negligible. So, the implementation in the code looks like this. Partial derivative of loss function with respect to x, which is delta L by delta x, is equal to delta L by delta y times 1 bracket x is greater than 0. This 1 x is greater than 0 is an indicator function. It acts as a gate. During the backward pass, the gradient coming from the upper layers flows straight through it if neuron was active or positive. During the forward pass, if neuron was inactive or negative, the gate slams shut. The gradient becomes 0. This simple gating mechanism is why ReLU networks are so sparse. The gradient only flows through the active path of the network, effectively training a smaller, leaner subnetwork for each specific input example. This is distinct from sigmoid, where the gradient flows through everything but gets diluted and weakened by every step. ReLU doesn't dilute, it selects. It chooses which weights to update and which to ignore. Understanding this selection mechanism is crucial for debugging. If you monitor your gradients, which you should be doing, and you see entire layers with zero gradient, you know that you have a dying ReLU problem. You know the gate has slammed shut and isn't opening back up. That is your cue to lower your learning rate or switch to leaky ReLU. We have covered a massive amount of ground in this episode. Let's simplify it into a cheat sheet for your projects. If your project is for binary classification output, use Sigmoid. It is the only one that gives you clean 0 to 1 probability. If it's a multi-class output, use softmax, which we'll cover in a dedicated video as it's a generalization of Sigmoid. If it's a hidden layer of a standard feed-forward network or a convolutional neural network or CNN, start with ReLU. It is the industry standard for a reason. It is fast and robust. And if your gradients are dying, switch to leaky ReLU. In transformers or LLMs or large language model, use GELU or Swish. The smoothness matters when you have billions of parameters. In RNNs or LSTMs, stick to Tanh or Sigmoid. Their gating mechanism rely on a specific 0 to 1 and 1 to 1 ranges to control memory flow. Understanding activation function is difference between blindly importing libraries and actually being a deep learning engineer. These functions are the vocabulary your neural network uses to express complex ideas. If you limit the vocabulary, you limit the intelligence. If you found this deep dive helpful, hit that subscribe button. Drop a comment below like non-linearity is a key. So I know you made it to the end of this lecture. I'll see you in the next one. Keep coding.